So we continue our solution to exercise 12.2.3, and where we are proving that theorem. We have proved many parts, but two parts are still there, parts G and H. So this is part G. As usual, X is a metric space with some metric D. Now in X we have a collection of open sets. It's a family of open sets, an indexed family where I is the index set, and for each alpha in I you have an open set E alpha in X. Then we have to prove that their union is also open. Just like that, we have an indexed family of closed sets F alpha, where each F alpha is closed, then their intersection is also closed. So let us first prove these two things. We start the solution by first giving a name to this union. Let's call it E, because it's cumbersome to keep writing this notation. And then we take an arbitrary point X in E. Now because E is this union, so X will belong to some E alpha. Then X belongs to E alpha for some index alpha in the index set I. But E alpha is open, and so some ball centered at X will be entirely contained in E alpha by a previous part of this same theorem. And that ball will have some radius, which is some positive real number R. But then if this is a subset of E alpha, then this obviously is a subset of E as well, because E alpha being one of these sets is itself a subset of E. So that way we find that there is a ball, an open ball centered at X having some radius that is entirely contained in E. And hence, again, by a previous part, which part I am not going to tell you, one of the parts that we proved earlier, by that part, every point in E is an interior point, and that is why E is open. This second part involving the closed sets F alpha, we do not use elements or anything. We are going to use the previous part, that is where we proved that the union of all the E alphas is open. So this time also we give some name to the intersection. This time we are considering the intersection of all the F alphas. Let's call it F. Now it is given that each F alpha is closed in X. So by a previous part of this theorem, these complements, each one of them, complement of F alpha in X, each one of them is open. So by what you did just now, the union of all these X difference F alphas is open because each one of them is open. This union, however, by general De Morgan's law, is the complement of the intersection. That means this is just F here. So that is open. In other words, X difference F is open, and that is why by a previous part F is closed. That's it. And finally we have part H. This is the last part of that theorem. It states that for any subset E of X, for any subset E of our metric space X, the interior of E is the largest open set contained inside E, and the closure of E is the smallest closed set containing E. So we start the solution by taking any subset V of E which is also an open set in the underlying metric space. And then we take any point V in V. Because V is open, there will be a ball centered at V having some radius R, which will be entirely contained inside this set V. And because V is itself contained in E, so that ball is also contained in E. And we have completed the sentence here by writing for some positive real number R, which is the radius of this ball. Now because such a ball exists centered at V, which is entirely contained inside E, so by the definition of interior points, V is an interior point of E. That is, V belongs to the interior of E. So any point in capital V is inside the interior, so V is a subset of the interior of E. So do you see what we have shown here? We have shown that if E has an open set inside of it, then that open set also has to be inside the interior of E. Okay. And the next thing we want to show is that interior of E is itself an open set. For that, next we proceed like this, where in this part, this leads to this. So W is also contained in the interior of E, where W is the union of all the open sets contained in E. That means W is the union of sets like V. Note that W itself is open. By which result? By the previous part, because W is a union, some union of open sets like V. But now, how do we use this to show that interior of E itself is open? Let's see. Now for any element E in the interior of E, there exists a ball BE, S centered at E, which is entirely contained in E for some radius S, which is a positive real number. But why? Well, that comes from the definition of interior point. Small e being in the interior of capital E means that small e is an interior point of E, and that just means existence of such an open ball, such a ball centered at that element or point E having some radius which is entirely contained in E. This is what being an interior point means by definition. But then we write, since E belongs to the ball centered at E contains E itself. Why? Because the distance between E and itself is 0, and obviously 0 is less than S. That is why by the definition of this ball, E itself is contained in this. And because this ball is a subset of W, that is why E being an element of this and this being a subset of W imply that E belongs to W. Where is this coming from? That the ball is contained in W, we have written by part C. What does part C say? If you go back to the statement of part C, it tells us that any such ball is itself an open set. And what is W? W is the union of all open sets contained in E. This is an open set contained in E. So that means W has this set also. I mean, when you are taking the union, this is one of the sets, and that is why this is contained in W. So that way we find that E belongs to W. So any point in the interior of E is also contained in W. So that way the interior of E is also a subset of W. Now if you combine this containment and that containment, you get the fact that interior of E is equal to W. But as I said just now, W is open, being a union of open sets. Interior of E now itself becomes open. And already we know another fact, even before doing these things, that the interior of E is itself a subset of E. So what do you conclude from all this? The fact that interior of E is contained inside E as a subset, and now the fact that it's also open, tells you that it is an open set contained in E, and it contains all other open sets V which are also contained in E. So in that sense, it is the largest open set contained inside E. Now in this second part, we have to prove that the closure of E is the smallest closed set containing E inside of it. Okay. So for that, what we do, we take a closed set K which contains E inside of it. Alright. And then we take any point X in the closure of E closure, E bar. For such a point X, there exists a sequence of points Xn in E, which means that all these Xn's are points in E. which converges to X by proposition 12 to 10. You go back to this and there you will see that X being inside the closure and a sequence like that existing are equivalent to each other. Now we note the fact that then this sequence Xn is also a sequence in K. Why? Because each Xn is a point in E and E is a subset of K, that is why. So each Xn becomes a point in K as well, and it is given that K is closed. So that is why if you go back to part B of this proposition or theorem, whatever it is that we are proving, that would imply that X belongs to K. What that part says is this: if you have a sequence of points in a closed set which is converging to some point, then that limit has to belong to that set, that closed set. And here that sequence is this and the limit is X. So that is why closedness of K forces X to be inside K. But what is X? X was any element in the closure of E. You have found that that also has to be in K. So that is why K contains the closure of E. So what is it that we have shown here? We have shown here that if our metric space has a closed set, any closed set which has E inside of it, then it also has E closure inside of it. So E closure in that sense is smallest. It's inside every closed set K which contains E. But now there is one more thing that we have to prove, namely that E closure is itself a closed set. If we manage to show that, then it will be the smallest closed set containing E, because not only will then it be closed, but it will also be contained inside every closed set that contains E. So next, our focus is on showing that E closure is a closed set, and we are going to apply the definition itself. That is, we take any point Y in the boundary of E closure, del E bar. If we can show that this Y belongs to E bar itself, then by definition E bar will be closed. Now what does it mean for a point to be in the boundary of a set? It means that it is neither an interior point nor an exterior point. In particular, it means that if we choose any positive real number epsilon and consider the ball centered at that point having radius say epsilon divided by 2, this is only a convenience for calculation. Okay, if you want, you can just take epsilon here as well, but for some reason I have chosen epsilon divided by 2. You will see why. This ball will intersect the set whose boundary you are considering here, and that set is E bar. Actually, this ball will intersect both E bar and its complement, but this is what we need. So this intersection is non-empty. That means there is something. Let Z be a point, let Z be something in this intersection. Now note that Z belongs to the intersection of this ball and E bar. So that means Z after all belongs to E bar. But what does that mean? It means that Z is an adherent point of E, of the set E. Why? Because the closure of E by definition is the set of all adherent points of E. And that's why this time if you consider the ball with that same radius but centered at this Z, which is an adherent point, it has to intersect E. The reason for this intersection being non-empty and this one being non-empty are slightly different. This one is non-empty because Y is a boundary point of E bar. This one is non-empty because Z is an adherent point of E. But it is non-empty, that one is also non-empty. So that means in this intersection also there will be something. So let W be a point in this intersection. Now you look at this calculation. We have considered the distance between Y and W. Why, that you will understand. by the triangle inequality which every matrix satisfies, this is less than or equal to the distance between y and z plus the distance between z and w. Now this distance is less than epsilon divided by 2 y. That comes from this fact. Because z belongs to this ball, by the definition of this ball, the distance between z and the center of the ball, which is y, is less than the radius, which is epsilon divided by 2. Just like that, the distance between z and w is also less than epsilon divided by 2 because of this. W belongs to this ball, so the distance between w and the center of this ball, which is z, is less than the radius, which is epsilon divided by 2, and their sum is epsilon. So what have we found? We have found that the distance between y and w is less than epsilon, and that is why w belongs to the ball centered at y having radius epsilon, but at the same time w also is in E, so w belongs to this ball and E. That means it belongs to the intersection of these two things, and that implies that y is an adherent point of E, or in other words, y belongs to the closure of E, y. You go back to the definition of adherent point. What is y actually? Originally y belongs to the boundary of E closure, and then by doing all these things, we found that this ball centered at y, dy comma epsilon, intersects E. At some point, at what point, that does not really matter. The main thing is that this intersection is non-empty. Or in other words, we have shown that any ball centered at y intersects E. Where is this any coming from? Any epsilon. Any ball centered at y means having some radius, any radius, which is a positive real number. So by the definition of adherent points, y is an adherent point, and that's why it belongs to E bar. But do you remember that just now I said that if we can show that y belongs to E bar, then by definition E bar will be closed. Why? Because this means, the fact that any point in the boundary is also in E bar means that E bar contains all of its boundary points. So by definition it is a closed set, and that's what we wanted to show. So this is where the solution ends, and the proof of that result also finally ends. There is one more exercise which is whose solution is very short, it's small. So let's do that also. So next we have 12 to 4. Let x comma d be a metric space, x naught be a point in x, and r be a positive real number. Let us consider these two sets. Looking at B, you understand that this is nothing but the open ball centered at x naught having radius r, and C is the closed ball, its closed version. This one consists of all points x in the space such that their distances from x naught are all less than r, and in this C we have those points whose distances from x naught are less than or equal to r. So automatically B is a subset of C, obviously just from the definition, but we have to show that B closure is also a subset of C. That is part A, and this is part B, where we have to give an example of all these things such that B closure is not equal to C. So this is the solution to part A, very short. By proposition 12 to 15C, it is in fact this proposition, so it was not a theorem, it's a proposition that we were proving in the previous exercise. By part C, C is a closed set because every closed ball is closed. Just like every open ball, that is ordinary ball is open, closed balls are closed. Alright, and just now we saw that B is a subset of C, and that is why by part H, what we proved today, B closure is a subset of C. Why? What does part H say? It says that E closure, where E was any subset in a metric space, is the smallest closed set containing the set E. In this case, C is a closed set containing the set B. So you think of B in place of E and C in place of that K, capital K that we saw there. C is a closed set, see, C is closed which contains B, and B bar by this part H is the smallest closed set containing B. So this being the smallest of all closed sets will be contained inside every closed set. In particular, it will be contained inside C. So that's how we have part A, and next comes part B. For part B, we consider the set of real numbers with the discrete matrix. So it becomes a discrete space. In this space, we take the point x0 equal to 1, and for the radius r also we take 1, and consider the open ball centered at 1 having radius 1. You know that in the discrete space there is only one real number whose distance from 1 is less than 1, because this discrete metric can only take 0 and 1 as its possible values. So the only point in this ball is the center 1 itself, nothing else. Anything else, any real number which is not equal to 1 has distance equal to 1 from 1, not less than 1. So less than 1 distance, that value is only 0 in this case, only possible value. So that is why you have this singleton set which is closed, and that's why its closure is equal to the set itself. You recall one of the parts of this proposition where we said that, actually we proved it, that singleton sets in any metric space are closed. It is from there that we are getting this equality. So the closure of this ball, that is this B bar, in this case is the singleton set consisting of 1. But what is the corresponding closed ball also centered at 1? It is by definition the set of those real numbers whose discrete distances from 1, this is the center, just like here 1 is the center, is less than or equal to 1. But all real numbers will qualify this, will satisfy this condition, because the discrete distance can either be 0 or 1. So anyway this inequality is true, and that is why this closed ball becomes equal to the entire set of real numbers. So here B bar is not equal to C. So that's where this section itself ends. All its exercises are also over, and in the next video on analysis we can start the next section on relative topology.